All right, lesson 135. This one's actually kind of a three-part lesson. They're going to hit on basically what they call wiring for the future, which in my mind that changes so fast you can't print that in a textbook. And then the second item is standby power systems, otherwise known as generators. And then lastly, we have what they call photovoltaic systems, or it's a kind of a fancy way to say solar electric systems. So I just want to focus quickly on the standby power systems or the standby generators, and then photovoltaic systems. There's a lot of different little stuff in here, and unless you kind of become working for one of these niche contractors, it's not really something you need to consider yourself an expert on any of these topics. But let's just hit the generators and solar electric systems here, just in brief overview so we can understand what's going on. So to start, let's look at a standby generator system. So this comes right out of your text. This shows essentially, here's a normal panel. They've put a 60 amp breaker in this panel. They've got a automatic transfer switch here in this case. So this thing will automatically detect if there is utility power. It will be oriented in this way. So this switch, this double pole, double throw switch is made this way. If it loses power, it'll sense that and actually switch. And we're going to look at what that looks like next. But then over here we have what they call a critical load panel board. So these are all the things you would want to have powered by your generator if power goes out. What we can see, if power is normal, our current flows in this fashion following that red line. So it's coming from the utility power. Notice we don't backfeed the generator. That's very important here as well. So let's say we have a power outage now. So what happens is, because notice this setup is automatic. Okay, so nobody's going to throw this main breaker. So we're still connected to utility here. So that's something to keep in mind. So as you can see now, this automatic transfer switch has now flipped here. And this doesn't have to be automatic. It can be manual as well. But a higher end one's going to be automatic. So now we can see our electricity flows in this fashion. It flows from the generator through these critical loads. Notice a couple key things. It doesn't power any of our non-critical loads, our normal circuits, because we don't want to overload our generator. But even more importantly, we're not backfeeding the grid. We're not going back onto the utility company. That's important for a lot of reasons. Number one, you don't want your generator powering your neighbor's house. But number two, it's also a major safety issue for utility workers. So we've got to make sure that we don't allow any opportunity for power at the generator to backfeed onto utility power, right? Again, that's a very brief overview of how it goes. Unless you find yourself working for a company that installs standby generators, a brief overview is going to be enough for you. So then I want to jump over quickly to photovoltaic systems. Again, that's just another way to say a solar electric system. So I've got kind of a one-line schematic here that I've made up. This shows you a bunch of PV panels, photovoltaic panels. They could be on a roof, they could be ground mounted. You're going to see, frankly around here, you're going to see a lot more ground mounted just because we have a lot of open fields and open spaces. But it doesn't really matter. The principle is going to be the same. So we've got our PV panels. They would call this an array when we get a bunch of them together. And in this case, we're using a setup which I refer to as a central inverter setup. So first of all, what's an inverter do? Well, it converts from DC power to AC power. So our PV panels are going to create DC power. We need to change that to AC power to be able to use it in our building electrical systems, right? So in this scenario, we have a central inverter. So one big inverter that's going to transfer all the panels' DC power into AC power. So as we can see here, let's get some electron flow here, is we've got all of our DC power from our PV panels coming down to what I call a DC combiner box. So essentially it's almost like a breaker box, except in a DC setup it's actually going to use fuses. But you can really think of it as a regular breaker panel, except where the typical load side of the breaker is, we're actually putting the wires from the PV panel onto the load side of the breaker and kind of back feeding the panel and then going down into one big feeder wire here. So you can think of these as a bunch of branch circuit wires. These are a bunch of feeder wires, except we're actually feeding sort of in the opposite direction, right? So anyway, then that gets to our central inverter, transfers it from AC to DC. keeps going up through here. We actually have this is nothing different than your regular utility meters, but this is, and the state of Pennsylvania actually requires it, but this meter is only measuring our solar power. What power are we creating by solar? And the reason that's important, because there's naturally a lot of incentives, and you can literally sell power back to the utility company. So this is measuring how much we're actually creating. Notice the only power going through here is that created by the PV panels, right? So we continue on through a disconnect switch. That's simply a safety mechanism to isolate the utility power from our PV power. And then notice here they go through the disconnect switch into this is just your normal electrical panel now, and then out to your building loads. So this power is actually powering your building loads. But then the other thing we got to notice here is we still have, this is sort of your utility power, comes in through your normal, and this shouldn't say PV meter, it should say utility meter, but comes in through your utility meter and feeds your electric panel into your building electrical loads as well. So we're actually sending power into this electrical panel system from two different directions. The reason that's okay, and one of the things that this inverter does, is it has to see utility power as well, because it needs to match the sine wave exactly. Otherwise we would have a dead short here. But A phase coming out of this central inverter matches perfectly A phase from utility. Same with B phase, C phase if we have a commercial building. So that's the reason we can actually feed these from two different directions here and not have any kind of issues, because our inverter matches that sine wave, right? So with that said, if we lose utility power, our PV panels are no longer creating power. Well, the panels are still creating power, but the central inverter is not allowing power through because it doesn't have that utility power to match the sine wave with, so it just shuts down. So it automatically will kill power when we have a utility outage, which goes back to the fact that we don't ever want to allow our power to be back feeding the grid if somebody could potentially be working on that line, right? So we can think about this, if we're creating more power than we're using here, this power would actually run back on the utility line. So we're not pulling any power in, we're actually pushing it back out. If the utility is energized, that's not an issue. If somebody's going to come to work on that thing, now we do have an issue. And again, we need to make sure we're not back feeding that grid when they're expecting it to be powered off, right? And I do have one more setup here. You notice not a whole lot changed. So what did we do here? We have, in this case, PV panels, DC combiner box, central inverter. Well, what do we change here? Well, we lost our central inverter, and we now have an AC combiner panel. So what's going on here? We're now having a setup which I think is probably the most common, which is PV panels with micro inverters. So every PV panel is going to have its own small inverter underneath it. So we're now straight from the panels sending power to that micro inverter on the panel itself. Out of there, now we're sending AC power. So now we're just sending it to an AC combiner panel. This is literally just an electrical panel, but we're feeding it in the opposite direction. So these branch circuits are actually bringing power in, combining to one feeder circuit which sends power out. We don't need that big central inverter anymore because we have the micro inverters. We're going to go straight through the PV meter into the disconnect switch. So beyond that is exactly the same as what we just looked at. So I do have one more video. It's going to be a separate link on the LMS. We actually got out to an actual PV install. I took some video of the system to try to show you these parts in real life. Again, it's going to be a ground mount, and it's going to utilize micro inverters. So you will get to see sort of all these components set up and hooked up on an actual job. So be sure to check that video as well.